Okay, I'm going to try to do this problem really fast. I want to go through just the quick key reading points, and then I'm going to solve it as quick as I can. So we have a problem, water pumped into a tank at a rate. So that's the in amount of the water, and it's some exponential. We'll use our calculator we can for that. And then it says water is removed from the tank at R. So this is the removal of the tank. So one is a continuous function where we know the equation. The other one is differentiable and decreasing, so it's getting smaller. So it is also continuous because if it's differentiable, it has to be continuous. So this is a smooth curve, also decreasing. Okay, so selected values of the table shown above at time 0. Okay, that's important to note. 50,000 to start with. So 50,000 liters of water in the tank. Estimate R prime of 2. This is R. R prime of 2 would be the slope. To estimate, you're going to find the slope between R of 3 and R of 1. All over 3 minus 1. You go up there, find in those numbers, plug them in. This is 240 over 2, which is 120. Indicate units. That would be liters per hour. So that is our estimated rate at time 2 that stuff is going out. Part A. Part B. Use a left Riemann sum. 4 subintervals. Now we haven't done Riemann sums for a while, but you know how to do. And we're estimating the total removed from the tank during the 8 hours. So a Riemann sum is a totaling function. This is what's removed. If we're totaling what is removed, then we're going to add up all of those R of t dt's during that 8 hours. And it's going to ask you if it's an overestimate, underestimate. We're going to hurry up and not worry about that right now. So left Riemann sum, first interval is 1. The height is 1340. Second interval is 2. The height is 1190. Third interval is 3. The height is 950. And the fourth interval is 2. And the height is 740 because it's a left Riemann sum. Add all those up, you get 8,050 liters that were removed. And is an overestimate or underestimate? It says that this function is decreasing. So if it's a decreasing and we're doing a left Riemann sum, that's going to look like that. That's an overestimate because the function is decreasing. We're not important for what's on your test. Okay. Letter C. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So we have two things happening. We have water that is flowing out and water that is coming in. Plus we have the water we start with. So we go back up here. Water's pumping into the tank here. So the total amount coming in is the integral of 2,000 e to the negative t squared over 20. That's the amount that comes in over the 8 hours. Plus there's 50,000 that we started with. So that tells you how much is in the tank. If we didn't ever pump any out, that's how much would have the tank. And then from that, you have to figure out how much was taken out of the tank. Well, we know 8,050 was taken out of the tank. So whatever we get here, we subtract 8,050, and you get your number. This you do on your calculator. Boom. Put it in your calculator. 2,000 e to the negative x squared over 20. Probably the fastest way would be go to calculate integral and just enter 0 and 8. The other way you could do it is go to function int 0, 8. I got it stored in the y1 dx. Boom. 7836. So your total here is 57,836.195 minus 8,050. I'll let you subtract, find the answer. Okay, letter D. Is there a time t when the rate of the water in the tank is the same as the rate of the water moved to the tank? Okay, so in other words, sometime is the big R, is that ever equal to W? So R is the rate that big R moves. Is that the same as W? Well, if that were the case, then big R minus W would have to be equal to 0. Okay, this is a question. Again, this is a bigger question. You don't necessarily have to know this for your test if that's what you're worried about, but it's good. It's just good application here. So, in other words, somewhere are they the same? Do they cross paths? Well, the way you can think about this is R of 0. Remember, R is the removal. R of 0 is 1340. And it goes all the way to R of 8, which is 700. So that's a decreasing function. It's getting smaller. W of 0 W of 0 is 2000. If you plug in 0 into this equation right here, you get 2000 e to the just 2000. And W of 8, you can calculate on your calculator, is 81.5244. In other words, I'm plugging in 8 here for this value. Okay? So what is happening here is somewhere along the line we should have a crossing of our slope of the x-axis. So if our slope we're looking at is R minus W, or W minus R, either way, right here W minus R is positive. Okay, and W minus R is our change of rate we're looking at. Right here, W minus R is negative. And W minus R is the net rate. It's the water out, water in rate. So if the water out, water in rate goes from positive to negative, if we graph that slope positive to negative, then somewhere by the intermediate value theorem has to